So hello everyone, hope you are doing really good and welcome back to my channel. Today we are at the day 28th of the June Daily Leetcode Challenge, and let me tell you today we have very interesting question in front of us. So please open your antennas and be ready because it's really going to be an interesting question, and we're definitely going to learn something out of it, right? So I will first explain the question to you, and then we will understand which algorithm we are basically trying to implement it with. Okay. So what we are given is, okay, I will just try to zoom it first so that, yeah. So what we are given is, as you can see, it's going to be a graph question. Okay. What we are given is we are given the number of nodes in the graph, okay, and then we are given edges array which represents the edges basically, and then when we are given a array which will represent the probability behind each of the edge. Okay, for example, when I say 0 to comma 1, it means there is an edge between 0 and 1. You can clearly see it's an undirected graph. Okay, there are no direction in the edges. Okay, it's undirected graph. So 0 and 1. Okay, so when I talk of 0 and 1, you can see the probability for this edge is going to be 0.5. Okay, it's also written here. Now come to the case of 1 comma 2. So there is a edge between 1 and 2. It's an undirected edge. Okay, so we don't know whether it's going from 1 towards 2 or from 2 towards 1. Okay, we just know that the probability of the traversal to this edge is 0.5. Okay, now coming to 0 comma 2, you can again see the edge between 0 and 2. You can see here, and its probability is slightly different, which is 0.2. Okay, so these are the inputs given to us. I think each of the things are making sense to you right now. Okay, each of the things are easily understandable. Okay, now comes to the other inputs. Okay, there is a start given here. Basically, start refers to, first of all, try to understand there are three nodes. Right, there are three nodes in this graph. So 0, 2 and minus 1. Okay, 0, 1 and 2. Okay, so there will be a start node and an end node. Okay, so basically you have to start from this node marked 0. Okay, you can see as 0 is marked here, and you have to end the path at node marked 2. Okay, so you can see 2 is also here. So what we have to do, we'll see that now, but just understand these things. Okay, so these are the number of nodes, these are number of edges, there is success probability each of the edge. Remember, success probability is not associated with node. Okay, it's associated with each edge. Please make this point very clear when you talk of a graph. There are two things: number of nodes and number of edges. Okay, they can be very different, they need not be same or comparable, right? So the success probability is associated with each edge. Okay, not the nodes. That is something important. Then this is called start and end. Okay, we'll start a node marked like 0 here in this case, and we'll end at node 2. Okay, now let us see the question. So we are given an undirected weighted graph of n nodes, 0 indexed. Okay, represented by a edge list where edges of y is equal to a and b is an undirected edge connecting the nodes a and b with a probability of success of traversing that edge as success probability of y. Okay, so if I talk about the first element of this edge, it's between 0 and 1, and so the first element here will represent the probability of that edge. Okay, that's what they're trying to say. Okay, now come to the question again. Given to node start and end, find the path with maximum probability of success to go from start to end and return a success probability. Okay, I will again repeat. Given the two nodes start and end, find the path with maximum probability of success to go from start to end and return a success probability. Okay, if there is no path from start to end, return 0. Your answer will be accepted if it differs from the correct answer by at most 1 raised to power. So it's basically 1e minus 5. So basically it refers to 10 raised to power minus 5. Basically the last 5 decimal points of your answer. If it doesn't match, that's fine. But other than that, everything should match. That's what I'm trying to say. Okay. So yeah, that's the point. And before we begin, let me tell you this: we are going to solve it using the Bellman Ford algorithm. There are see many ways to do it, but why we are choosing Bellman Ford, I will just let you know. But just understand that we are going to use Bellman Ford algorithm. If you don't know what it is, I will give you some hints of it. Okay, you will have to definitely look out for it in Wikipedia and anywhere. Okay, in Wikipedia basically there is some animations also given how it works, so you can see that also. So let me tell you what is Bellman Ford. It's basically a single source shortest path algorithm. Okay, what happens is, suppose I start from A, so it will basically give me all the shortest paths from A to all the other nodes. Okay, which path I should follow? It will give me that from A to all the other nodes. So single source shortest path algorithm. There's another algorithm called Dixit-Ras algorithm. So basically, Bellman Ford is more slower than Dixit-Ras algorithm, but it's more robust. Why it's robust? The idea here is that it can detect, the cycle presence of cycles in graphs, and it can also deal with negative edge weights. Okay, so these are some of the points why it's really robust. But remember, because of these advantages, it is on the slightly slower side compared to Dixit-Ras algorithm. And in this case, you can clearly see they have nothing mentioned about cycle in this first example. So you can see there is a cycle present. Okay, there is definitely a cycle present. So we definitely need a way to mitigate this risk so that we do not end up in a cycle. Remember one point very clearly. See, these things you will learn by experience only. Right? We will see when you are trying to learn an algorithm for the first time, you will not know these things. Okay, that's why I've written it in capital letters. Remember, a loop do not increase the probability of reaching a node. Okay, of the probability of reaching a node. For example, if you talk about this, let me look. Let us deal with it, and then you will understand. See, let us say I start from zero. Okay, I go to one. I have probability of 0.5 now. Okay, then I go from one to two. I have probability of 0.5 into 0.5, which is 0.25. Okay, now 0.25. Okay, again multiply it with zero. So what the idea here is, see 0.25 into 0.2. Okay, 0.05. So basically, if you multiply, you will get to know that the probabilities are basically decreasing. Okay, because see, these numbers are smaller than one. Okay, you must be knowing that whenever you multiply a whole number with a number smaller than one, the answer will decrease. Okay, that it won't increase, it will only decrease. Okay, that's the basic idea. That's what I wanted you to convey. So the idea here is when you go around a circle, definitely you are not going to increase the probability, but basically you are trying to decrease the probability. Remember, a loop does not increase the probability of reaching a node. Okay, please make this point very very clear. So idea here is, see, we don't want to go through the loop again and again. Okay, we just want to go through the loop once. That's the basic idea, and that's why Bellman Ford algorithm is preferred here, because see, when you talk of Dikshitas and all those things, these does not work well with loops. Okay, that's the basic idea. But Bellman Ford algorithm will work well with loops. Okay, because there is a maximum threshold already set for the number of times we are required to go, and it will be going for that time only. We'll see that now in detail. So there are some terms associated with balance for orgasm. For example, the term relaxing. Relaxing basically means that, see, there is no order for relaxing. Please make this one very clear. See, when I was learning well informed, these things I was not knowing, but you are getting some guidance that should be beneficial for you, and it will take less time for you to learn. Remember, there is no order for relaxing. You can relax in any age, any time. Okay, any age, in any order you can relax. Okay, relaxing basically means that we are just trying to understand, if I go from zero to one. Okay, if it's like, see, parallel fold is basically it's finding the shortest distance. Okay, but in this case we are dealing with probabilities, so it will just add the distance and it will check. Okay, if it's shortest or not. That's the basic idea. That's what it is. But in this case we'll be manipulating it because we want probabilities. Okay, so I will just go to the solution now quickly. I hope these things are clear to you. But yeah, let us take this first. See, when I come from 0 to 1, okay, it is 0.5. Then when I go from 1 to 2, it is 0.5 into 0.5, which is 0.25. Okay? But I can also go from 0 to 2 directly with the probability of 0.2. Remember, 2 is the last node. Okay, so I need to find basically a path from 0 to 2 which has the maximum probability. So you can clearly see I have two options, either 0.25 or 0.2. Okay, so among the 0.25 is the highest. That should be the answer. That's what it is. And in this case, you can say start is 0 and at 2. Okay, again same values, 0.5 and 0.5. If you multiply that, it will get 0.25. But from 0 to directly it's 0.3. So 0.3 is greater than 0.25. So answer is 0.3. Okay. In this case, you can clearly see and is again a 2, but chart is 0. So basically, there is no way to reach 0. Sorry, 2 from 0. Okay. So the answer is 0. There is no probability as such. Okay? The path has 0 probability. That's what we are trying to convey. Okay? And yeah, that was all. You can see the time convex are slightly on the higher side. So now we'll continue with our solution. Okay, so some theory parts here, then we'll quickly jump to the code. The code will become very easier if you're clear with the theory part. Remember, we are going to implement Bellman Ford algorithm only. Okay, why Bellman Ford? Because here we have definitely seen that there is a chance of edge, and you can see the first example also that it's a circle present, right? There is cycles. Okay, so to deal with those things, we need Bellman Ford algorithm, right? So let us see with the theory part now. Probability of a path, okay, equals the product of the probability of its edges. Okay? So you can clearly see when I go from 0 to 2 along 1, what it is, I multiply the probability. Okay, 0.5 to 0.5, I get 0.25. Okay, that's what it is. Initially, we set the probability to reach the starting node as 1 and all other nodes as 0. What we are doing is, see, initially, we set the probability to reach the starting node as 1 and all other nodes as 0. So basically, we are going to maintain an array. Okay, see, this array will have probability, starting probability, okay, for each node. Remember, not for each edge. Remember, starting probability from each node. Okay, not from each edge. Okay, so basically I will have an array which will have 0, 1 and 2 only. Okay, so because the start is going to be from 1, sorry, from 0, so only for 0 the starting probability will be marked as 1. For all other nodes, the starting probability will be marked as 0. That's what I'm trying to convey through this. Okay, initially we set the probability of each starting node as 1 and all the nodes will be having a probability of 0. Okay, because the start is always going to be from the starting node. Okay, then we iteratively relax. This time I again and again repeat. So this time we will face a lot if you are dealing with Bellman Ford's algorithm. Please go through Wikipedia and try to see at least one animation of how it works. Okay. See, this algorithm is really nice. Okay, many graph questions can be solved using this algorithm. That's why I wanted to take this solution particularly. It's really easy. It looks hard. Definitely it looks hard. I'm telling this from my experience. But once you get through it, you will understand a lot. Other algorithm will become very easy for you. This is a very robust algorithm, and especially for cases where we have cycles. Okay? Then we iteratively relax the edges of the graph by updating the probability to each node if a higher probability is found. Okay? That's what this particular statement. I understand it's not very clear, but we'll get to know when we are dealing with the code. Next statement is very important part of Bellman Ford algorithm. See this number n minus one. Please highlight this also. See n minus one. This some relax. These things you will get to know. In depth of it. Why we are doing this when you try to understand what's Bellman Ford algorithm. Okay. The process is repeated n minus one times each, which is enough to relax every edge of every possible path. Okay, I will explain this part in depth. Try to understand there are n edges. Okay, in the question it's given that there are n edges. Okay, now try to sorry n nodes. Okay, whenever we have n nodes, the the minimum possible edges needed to connect all the nodes is going to n minus one. Okay, please try to understand how. See, for example, in this case, there are three nodes, right? The minimum number of edges required to connect all the nodes. For example, 0 to 1 and 1 and 2. These are enough to connect the edges, right? So basically, it is going to be n minus 1. Okay. So for n nodes, we require n minus 1 edges to connect them. Okay. This is the minimum. Okay. I'm not talking about the maximum. In maximum, we can have any number of edges, but in minimum, we require n minus 1 edges to connect them. Okay. That's what it's telling. Okay. And if we relax the thing n minus 1 times, which should be enough to relax every edge for every possible path. Okay, just remember this is the thing why it helps us in dealing with cycles. Okay, because we are going to for only n minus one time. So even if there is a cycle, we will not get will not endlessly revolve around the cycle. This is the highlight of that. Okay, this is the highlight of this algorithm. It will only process the nodes for n minus one. See, all the edges will be processed for n minus one times. Okay, we'll see that now. But yeah, this is the basic idea. Okay. Remember this thing I again repeat. Remember, it does not increase the probability of reaching a node. Okay. Now coming to the solution part. Okay. So this, as I mentioned, we will have a max probability array. This will be for each node. Okay. Now initially it will be zero for each of the node. Only for the starting node it will have a value of one. Okay. Then we are printing it. Then we will run this loop for the n minus one times. As I mentioned here, each edge will be relaxed for n minus one times. Okay. This edge loop will run for n minus one times. Now from here I will be going through each edge and relaxing it. Okay. What is the relaxing operation? We'll see that. But remember, each see this is loop is going to run for n minus one times. Now from this loop onwards, we are going to relax each of the edges. Okay. So this loop will basically run for n minus one times. Okay. This particular part of the code will run for n minus one times. Okay. See, this has update value also. See, has update basically means once we reach a stage after which even if we run this loop, there is no update to the values. That means we have reached a place where up values are not changing. That means we have to stop. So this is for that. Okay. Initially it will be zero, and finally we are going to check if has update has changed. See, it will change with updates. Okay, it will change with updates. If it has not changed, we are going to break out of the loop. Okay, that is the basic idea. And finally, we'll return the max probability of the end node. Okay. So let us see what happens here. So as I mentioned, this loop will run 5 minus 1 times. This from here onwards, we are see this loop will basically go through each of the edges. Okay, what are the edges? These are the edges. It will go through each of the edges and it will do an operation which is called as the relaxing operation. What is that? We'll see now. So as I mentioned, it is going through each of the edges. Okay, edges array. It will going through each of them. Okay, we are taking out the edges u and v. Okay, u and v basically represent that edge between u to v, which is bidirectional. Okay, then we are going to get the success probability for this edge. Okay, this is a success probability for this edge. Okay, from this, for example, for 0 1 this is a success probability, right? So we're trying to get the success probability of this is called path probability. Okay, then see there are two ways obviously. See, when I talk about u and v, there are always two things. Okay, either way I can go from u to v or I can go from v to u. Okay, that's what I'm checking. I'm multiplying the maximum probability of u. Okay, from where it is coming, this comes from this array. Okay, it's coming from this array. I'm multiplying the maximum probability of u with the pass probability. That means, see, I'm at one. I'm trying to come at sorry, I'm at zero. I'm trying to come to one. What will happen is probability of me starting at zero into probability of 0.5. Okay, that will be give me the probability to reach one. Okay, that's what I'm trying to check. If the max probability of u, that is the starting probability of u, multiplied with the path probability is greater than the probability of v. Okay, max probability of v. That means See, there is some probability of starting at 1 also. Okay, there is some probability of starting at 0. So, probability of starting at 0 multiplied with the path probability, either it's greater than or equal to 1 or not. That's what I'm checking. If it is greater than or equal to 1, this part of the code will be executed. Okay, so basically, this value will now be updated to this value. Okay, that's what we are doing. This value will now be updated to this value. Okay, so max path probability of v will be now changed to this value. Okay, this value then has update equal to 1. Okay, now we are going to take it first v to u. Okay, v to u. So now we are checking if max probability of v into multiply with the path. See, just the reverse of it. Okay, just the reverse of it. Here u was mentioned. Here now v will come. Okay, we are checking if it's greater than the max probability of v. Okay? If that happens, same thing will happen again. This value will be changed to this value. Okay, that's what we are doing here. And has update has been changed to 1. Okay, then I'm printing it for your convenience. Okay, after this loop ends. Okay, after this loop ends. Basically, we're checking if head update is equal to 0. That means there has been no update made. If no update has been made, then there's no meaning to go for another loop. That's why we are breaking out of it. Okay. See, there are many questions here. Now you will say that after we updated the probability of v, why should we? Why we are doing this? Okay, we could have done it expressively. For example, if this happens, then this should not happen like that. You could have done. So let me tell you. Let me tell you how it works. See, suppose the probability of u is 0 is 1, right? Probability of that node 0 is 1. So 1 into 0.5, this will also become 0.5. Okay, this will become 0.5 initially. Okay. Now, if you talk about the reverse, that is 0.5 into 0.5 will become 0.25. Okay? But it is 1. So it won't change. That is the basic idea basically. We are going to go from one side only. Remember, we are going to start from 0 only. That's why we are ensuring that we start from that by making it 1. Okay. The starting probability of start is made 1, rest all the nodes it is 0. So what will happen is we will be moving only from this 0 towards the other node. So that's how we are ensuring that. So don't worry. Once we have updated, this code won't be executed basically. Why? Because remember, whenever some value is there, right? Some value is there. We are multiplying with a number less than 1. What will happen is that value will decrease. That value will always decrease. Okay. So this whatever it is, this will be definitely will have a probability of less than 0.5. Okay. Then multiplied again with 0.5, it will have a even lesser probability. So you will not get updated. So idea here is when this part of the code gets executed, we won't be executing this part of the code. That's the basic idea. See, the case of loops, it's a bit different. But remember, as I mentioned, this will run only for n minus one time. That's how we are trying to basically avoid the case of a loop, right? Basically, the case of a cycle. That's how it is. And finally, see, this is called the relaxing operation. Okay, this is what is called the relaxing operation. Operating each edge. See, in case of real Bellman Ford, we'll have a plus sign here. Basically, we're adding the cost of each edge. Basically, along as we travel. That's what it is. But in this case, we are dealing with probabilities, so we are multiplying basically. Okay. And at last, see, the idea here is, see, after doing it for n minus 1 times, basically see, for example, after running this loop for the first time, what will happen is definitely all the edges which are edges and neighbors of 0 will have some probabilities, right? Similarly, at the edge of the end of the second loop, all the edges which are at distance, after a distance of 2 edges from the node 0 will have the correct probabilities. That's what it is, right? This way we are doing it, and this greater than this thing, we're ensuring that we only update the maximum probability. Okay, we don't make it smaller at any instance. Okay, that's what it is. So at the end of it, when we come out of this double loop, what we'll have is we are trying to return the max probability of end. Okay, this is the array. Okay, from this we are going to the index of end, and we are returning its probability. That's what it is. So this is the Bellman Ford algorithm which we have modified to accommodate this question, and finally we are returning the max probability of reaching that node. Okay, so remember, see, why we are making it 0, the idea is because we don't want the loop to start from them. Okay, that is the calculation start from there. Okay, that's why only from the starting node we have made it 1. Okay, that's the basic idea. And if you talk about the time and space complexity, it's a bit easier here because see, what happens is I am going to relax all the edges n minus 1 times. Okay, what are the number of edges? Let m be the number of edges. In that case, each edge will be relaxed n minus 1 time. So basically, the time is going to be O of n into m. Okay, and because we are having an array to store the starting probabilities of each node. Okay, each node, so the space complexity will be of n. Okay, that's the basic idea where n is the number of nodes. Okay, so yeah, friend, that was all for this. Please pay attention to these algorithms. These are really beneficial, and this will really help you to solve questions. Okay, see, remember, this question can also be solved using the Dixitras algorithm, and there are other ways also. But why I use Bellman Ford is because, see, this kind of robust algorithms, because in graphs or in interview sessions, wherever you are, see, always, even if you're given a simple question, there will be always a question like, if there are saggles present, what you will do. So that's why I thought of taking such algorithm and explaining it to you, so that you will see, even if you're not aware of what Bellman Ford is, at least now you should know that it's really robust in case of in cases where there is cycle present, right? And how it's avoiding that, this how it's avoiding that, because it will repeat it only for n minus one time, because the election will happen for each edge only for n minus one time. So in this way we are avoiding any infinite loop going around a cycle which is present in the loop, right, in the graph. So Yafin, that was all for today. So if you really like my solution, please comment on the video, and if you have any doubts, we can always discuss further, right? See you tomorrow.